Hello everyone, welcome back to the lecture today. So this lecture will mainly focus on probability and the basic concepts in probability. So welcome back to the statistics teacher. So let's start this lecture. So in the outline of this lecture today, we'll talk about introduction to probability, views on probability, set theory basics, elementary properties, calculating probabilities. We'll also do mainly one of the most important concepts in medical probability, which is called Bayes' theorem, and how do screening tests use Bayes' theorem. And then we'll talk about ROC curves. So let's start with the learning objectives for this lecture. So in this lecture, we'll try to define and distinguish between objective and subjective probability, explain elementary properties including mutually exclusive and independent events, calculate probabilities using addition and multiplication rules, apply Bayes' theorem to medical screening, and finally, we'll try to compute and interpret sensitivity, specificity, and predictive values. So let's go into this lecture. So the first topic is the introduction to probability. So why do we use probability in the health sciences? So probability is the foundation for statistical inference. So if you remember inference, so inference refers to drawing conclusions about a population. So it refers to drawing conclusions. So whenever we try to draw conclusions about anything, we need to have the sample. So from the sample, we basically draw conclusions about population. So for this, it is important to know probability. Second is the concept of uncertainty. So medical diagnosis and prognosis are generally deterministic. So they are generally probabilistic and they are rarely deterministic. The main reason for this is because no one can clearly explain that their diagnosis is 100% true or is going to be 100% false or a certain percent true, a certain percent false. So it's all basis of trial and error. We can always use probability to justify the level to which or the level of confidence in the decisions made by doctors. So third is the concept of quantification. So here we move from what might happen to a specific numerical risk. For example, if a doctor says there's a 5% risk of complication, which means that out of the 100 patients that might have gotten that procedure, 5 of them might have gotten complications in that. So from the literature. So this would be, for example, from literature, or sometimes this can be from the doctor's intuition itself. So which brings us to the concepts of subjective and objective probability, which we'll discuss in the next coming slides. So the key insight to remember is that statistics allows us to quantify the uncertainty inherent in biological variability, and probability is basically the metric of that uncertainty. So it basically is the measure of uncertainty that we generally need to measure. So let's move on. So there are two views of probability. So one, we call it the objective probability. Second is the subjective probability. Objective probability is based on repeated trials or physical characteristics of the system. So things like classical probability, which is a priori probability, and relative frequency probability, which is a posteriori probability, are generally called objective probability. Second is the subjective probability. This is based on individual's person's belief or expert opinion. We generally use subjective probability rarely, and we only use it when the data is scarce, because the main problem with subjective probability is that it incorporates intuition and experience and not raw and measurable quantities. So let's start with objective probability. So the first one we're going to talk about is the classical probability, so also known as the a priori probability. So it generally assumes that all outcomes are equally likely. So which means that if any one of those events can occur, it can occur equally. For example, if a population has equal distribution of 4 blood types, let's say A, B, AB, and O, the probability of picking a person with one of those blood groups is 1 over 4. So it basically takes probability and converts it into a simpler formula, is basically saying the number of favorable outcomes over the number of possible outcomes. So this is how we define probability for objective or the classical definition of probability. So what happens here is that we always assume that all people are going to have equally likely blood groups. So whenever we calculate the probability of one of those blood groups, we are going to say that it's 1 by 4, which is one likely event out of the 4 possible events. So which is going to be around 0.25 or 25%. So limitation is that in medicines, outcomes, so things like surviving surgery or not, are rarely equally likely, and we cannot use classical probability in these particular situations. So the second one is the relative frequency probability, also known as a posteriori probability. Generally depends on the repeatability of a process. So which means that if an event occurs m times in n number of trials, then the probability of that event is m, which is the number of outcomes that it has occurred over the total number of trials n. For example, if 15 out of the 100 patients develop a side effect, then the probability of the side effect is the amount of times the side effect has occurred over the number of trials that you're taking into consideration. So which is written as 0.15. So subjective probability is used when processes are not repeatable or data is unavailable. So this represents the strength of belief. So for example, a clinical judgment saying, for example, a physician might say that there is a 70% chance this patient has condition X based on their unique presentation. So clinical judgment generally is used initially when there is no data present, and it generally is used when we have subjective probabilities, and these subjective probabilities are generally used in the Bayesian approach to often form the prior probability in Bayesian analysis, which is then updated with the data that is available. So the next one is the concept of sets and elements. So before we go into the actual probability, let's understand some of these set elements. So a set is a well-defined collection of objects, distinct objects. For example, all patients with diabetes are examples of a set. So an element is a single object in a set. A universal set is the set of all possible elements in a context. For example, if there are n number of ones in a universal set, then there are some of them that pertain to that particular set A. So U represents all the available elements or all the available objects in a context. So let's start with the first one, which is the union of sets. So this is where the set of elements belonging to set A, they can belong to set B, or they can belong to both. So this is generally written as A. This is the symbol union. So generally spelled out as A union B, or we can also write A or B. So the shaded region represents the total part. So which means that this entire region represents A union B. The intersection of sets is where the set of elements that belong to both set A and set B. This is where we use the key phrase A and B. So which means the intersection is what represents the overlap. So the overlap is what represents the intersection. So which brings us to some of the important events that we generally need to remember for probability. So the first one is mutually exclusive or disjoint sets or disjoint events. So these are two events. For example, let's consider two events A and B. They are mutually exclusive if they cannot occur at the same time, which means that they cannot have any overlap. So their intersection is a null set. So A intersection B is equal to phi. So phi here represents a null set, which is nothing but a set without any elements. So here essentially if you draw a Venn diagram, then the A and B are two distinct events. They cannot be both at the same time. So an example of this is that a patient cannot be both alive and dead at the same time. So which means that they can either be alive or be dead. So there is no state where they can be alive and dead at the same time. So now let's go into some of the elementary properties of probability. So these are what we call the fundamental properties of probability. So given a set of mutually exclusive events, E1, E2, and so on, En, that cover all possible outcomes, the first one to remember is probability of any event can always lie either between 0 and 1 and including 0 and 1. So probability is always between 0 and 1. Second is the sum of probabilities of all possible outcomes is always equal to 1. Third is for mutually exclusive events, the probability of two events, so EI union EJ, which is the inclusion of these events or the union of these events is equal to the sum probabilities of the individual events. So the reason for this is because remember that for mutually exclusive events, the probability of EI intersection EJ is always equal to 0. So because there is a null set, so the probability is always equal to 0. So the next one is, what is the difference between independent and mutually exclusive events? So even though these look like the same, they are the same concept, they are not the same concepts. So mutually exclusive refers to the occurrence of A that prevents the occurrence of the second event B. So which means the probability of the event being occurring A and B is always equal to 0. The independent effect is basically that the occurrence of one event has no effect on the occurrence of the other event. So here probability is not dependent on the other event being occurring or not. So if A and B are mutually exclusive and probability is greater than 0, they are dependent because A happens, so B cannot happen. So which means the information has changed. So there are three types of probabilities to remember. So consider two events, A representing hypertension and B representing obesity. So the first one is marginal probability, which is the probability of one event or a single event occurring. So for example, this can be things like the probability of occurrence of hypertension or the probability of occurrence of obesity. Joint probability is the probability of both occurring simultaneously. So this would be A intersection B. So this is the probability that both events occur simultaneously. And last one is conditional probability, is the probability that one event occurs given that another event has already occurred. So remember that this forms the basis for the next event to occur. So which represents the conditional probability referred to by A by B. So one of the first important rules to remember is the addition rule. So this is used to calculate the probability of A union B or A or B. So this is given as probability of A plus probability of B minus the probability of A intersection B. For mutually exclusive events, because of the fact that the A intersection B is a null set, the probability of A intersection B becomes 0. So therefore the probability of A union B becomes probability of A plus probability of B. So why do we subtract probability of A intersection B? If you remember that when we calculate A union B, so we generally double count the intersection because there are two intersections on both of these sets, once in A and once in B. So we subtract it once to correct for the total sum. So the next one is the multiplication rule. So this is generally used to calculate joint probability. So the formula is A intersection B is equal to probability of A times probability of B by A. So which is that probability that B occurs if A has already occurred. Or you can also write it as probability of A intersection B as probability of B times the probability of A by B. So for independent events, because of the fact that the conditional probability is not dependent on the other event occurring, probability of B by A becomes probability of B. So therefore A intersection B is just the multiplication of probability of each of those events. How do we calculate conditional probability? So we can just rearrange the multiplication rule, which gives us the formula for probability of A by B, which is probability of A intersection B divided by probability of B. So what this does is it effectively shrinks the sample space from the universal set to the set B. So which basically means that B becomes the universal set for this particular probability. So how do we visualize the conditional probability? So what does it say is that given that B has already occurred, what we generally do is we ignore everything outside of B and we only calculate the probability of A in the ratio of the intersection to the probability of B, which basically means that we are basically calculating this part out of the whole of B. So which brings us to the Bayes theorem and medical screening. So the medical screening problem basically is that we generally use tests like MRI, blood work and biopsy to determine disease status. So tests, because of the fact that they are rarely 100% accurate, we need to know what are the chances that if you have a patient that tests positive, what is the probability that they actually have the disease. So the notation we are going to use for this is D represents disease present, D bar represents disease absent, T plus represents test positive, and T minus represents test negative. So the test characteristics are generally determined by two particular quantities, sensitivity and specificity. Sensitivity is also called as the true positive rate. It is the probability of testing positive given that the disease is present. Again, remember, sensitivity is nothing but conditional probability, which basically states that the test is positive provided that the person already has the disease. Specificity refers to also what we also call the true negative rate. This is the probability of testing negative given the disease is not present or disease is absent. So we generally write it as probability of T minus divided by D bar, representing the fact that there is no disease. So what are the two false results that you end up getting in any test? So one is the false positive, the other is the false negative. So false positive occurs is just nothing but the probability of test being positive when the disease is absent, and false negative refers to the probability of test coming out negative when the disease is present. So remember, false positive is test positive when disease is absent. So when you don't have the disease but you test positive. So T minus, so false negative is you test negative when the disease is present. So this is what I mean by false negative. So if it's test positive when you have the disease, we call that true positive. If the test is positive but there is no disease, we call that false positive. If the test is negative but you have the disease, that's false negative. And when you don't have the disease and you test negative, that's true negative. Okay. So now let's go into the next one, which are the predictive values. So these are probabilities that are clinically useful to the patient. So there are two predictive values. One is PVP, called the predictive value positive. So which is the probability of disease given a positive test, and predictive value negative, which is that the probability of not having a disease provided you have a negative test. So what does the Bayes theorem tell us is the Bayes theorem provides us a way to derive the reverse of this formula by using the original formula. So which is probability of disease when the test is already positive. So this is written from the multiplication rule, so which is D intersection T plus divided by probability of T plus. Now, because of the fact that you already have the probability of D union D intersection T plus, which can also be written from the multiplication rule as probability of T plus over D times the probability of the disease divided by the probability of T plus. Now, the probability of T plus is the total probability of all the people that have the test positive. So this can be both the probability of people that have the test when the disease present times the probability of the disease plus the probability of people who have the disease but who test positive but don't have the disease times the total probability of not having the disease. So remember, this is nothing but you're calculating two formulas together. So which is basically saying probability of T plus intersection D and probability of T plus intersection D bar. So which is where we get the formula from before. So let's go back to that formula. So now you replace that formula here. Notice that there are formulas that you can use right here. So this is sensitivity. This is nothing but 1 minus sensitivity. This is prevalence. And this is 1 minus prevalence. So these are all the formulas that we have. If you remember, T plus over D bar, remember that that's, so D plus over D, that's sensitivity. Now, so based on the values that we have right here, so we can also note that this is T plus over D, this again is sensitivity, and D, probability of the disease, that's referring to prevalence. So rewriting everything, we have this formula right here, where P of D is nothing but prevalence. Prevalence is nothing but the prior probability of the disease, which basically says what is the chances that the disease is present in the population. So what is the probability of the disease in the population? Now, so replacing the formulas, we can always calculate the values right here. So this T plus over D bar can be rewritten as false positive rate, which is nothing but 1 minus specificity. So which can also be used in this particular problem right here. So I'm sorry, this is supposed to be 1 minus specificity in the previous slide. So we can also use that in the formula. So now let's use this formula in a problem, and let's see what the impact of prevalence is first before we go to the problem. So the prevalence P of D dramatically affects the predictive value positive. So a rare disease requires a very specific test to avoid high rates of false positives. So for example, let's take a scenario of a test that has 99% sensitivity and 99% specificity. If the prevalence is 50%, then the predictive value becomes 99%. If the prevalence is 0.1%, then the predictive value becomes 9%. So this is the probability 3 that we generally use to calculate these values. So from the population, you have the prevalence, which gives us the number of people who have the disease, and 1 minus prevalence, which becomes the number of people who don't have the disease. From the people who have the disease, you basically calculate sensitivity by calculating how many of those people will test positive. So that becomes our true positive. And how many people will test negative, which becomes our 1 minus sensitivity, which becomes the false negative. So from the people who don't have the disease, you calculate how many of them are going to be negative testing. So that's going to be true negative. How many are going to test positive becomes the false positive. So let's take an example. So data here states that the prevalence in the population is 2%. The sensitivity of the test is 95% and the specificity is 90%. So here the question says, if a patient tests positive, what is the probability that they have glaucoma? Remember that this is the prior condition. So which means the probability that they are being asked to calculate is the conditional probability, which is nothing but the probability of the disease being present provided that the test is positive. So this is nothing but the predictive value positive. So the predictive value positive can be calculated from the formula sensitivity times prevalence divided by sensitivity times prevalence plus 1 minus specificity times 1 minus the prevalence. So which can be used in this formula. So now use this formula and try to solve for the predictive value positive. So pause here for 2 minutes and try to solve this problem. All right. So if you want to solve this problem, the numerator here is calculated by you calculating the true positive, so which you can calculate right here directly. So if you want to calculate using the formula, So you can just use sensitivity right here. So which is 0.95 times 0.02 divided by 0.95 times 0.02 plus 1 minus specificity is 1 minus 0.9 times 1 minus 0.02. So which becomes 0.95 times 0.02 divided by 0.95 times 0.02 plus 0.1 times 0.98. So the total answer that you will end up getting at the end is 0.162. So even with a 95% sensitive test, a positive result only means a 16.2% chance of actually having glaucoma because of the fact that the disease is rare. So the rare diseases tend to have very high false positive rates, and common diseases tend to have very high false negative rates. So there are chances that you might end up having more false negative cases. So in simpler words, for rare diseases, so which is where the prevalence is very low, the predictive value positive is going to be low. Okay. So which brings us to the next problem. So of using probability now. So what do we have here? So we have 150 patients with high salt diets, 100 patients that have hypertension, 60 patients that have both hypertension and high salt diets, and the total number of patients is 500. So the first one you need to calculate is the probability of the patients with hypertension. So first thing we need to calculate is how do we calculate this? So remember, it's always part by total. So the part is the number of people with hypertension, so that's 100, and the number of people that are having hypertension, so total number of patients is 500. So your answer is 0.2. So to calculate P of H over S, so we calculate the probability of H intersection S divided by the probability of S. So the probability of H intersection S, which is nothing but S intersection H, is 60 patients divided by 60 divided by 500 in total divided by the probability with high salt diet, which is 150 divided by 500. So 500, 500 gone. So we're going to be left with 60 over 150, which becomes how much? So 0, 0 gone. So 2, and this is 5. So I basically divided both of them with 3. So 2 by 5 is 40% or 0.4. So the first thing that they ask is, are they independent? So how do we find whether an event is independent or not is basically by finding out whether the probability of H by S is equal to probability of H, right? So the probability of H by S, notice, was 0.4, while the probability of H is 0.2. So which means that they are not equal. So therefore, they are not independent. So this is a quick way of calculating independence for these events. So try this problem. So this is a problem again of prevalence, sensitivity, and specificity. So we have the predictive value positive given right here. Remember, you can always use the formula that I've given you. So rather than calculating in a different way, that is provided in the slide. So on the last topic is the ROC curves, or the receiver operating characteristic curves. So these are tests often output as a continuous value, not just a yes or no answer. we generally must choose a cutoff point, and these ROC plots generally provide a plot sensitivity and 1 minus specificity. So where we have 1 minus specificity on the x-axis and sensitivity on the y-axis. So if you choose a random guess, this is the line that you would expect to get. A good test must be much higher above the particular random guess. So 1.0 on this particular area under the curve is perfect. 0.5 is basically useless. So most tests tend to have the area under the curve ranging from, a good test ranges from 0.8 to 0.9, but an average test ranges from 0.6 to 0.7. So in summary, these are the key formulas that we have used in this particular lecture today. So these are the take-home points. So probability quantifies the uncertainty in medicine. So we distinguish between the mutually exclusive and independent events. The screening test that must be evaluated in the context of disease prevalence using the Bayes theorem. And high sensitivity does not guarantee high positive predictive value if the disease is rare. So thank you for your time today. So if you haven't subscribed, please subscribe to this channel and please provide your support for continuing these lectures. So thank you and have a great day.